Welcome to another Coding Like Mad MATLAB tutorial. In today's tutorial, we're going to be talking about convolutional neural networks. A convolutional neural network is a specialized type of neural network which takes as input an image or a frame from a video and gives as output an answer to a question like, is a particular object present, or where is a particular object in this image? This technique is actually going to be ubiquitous in the future because it underlies things like self-driving cars. Now, if you haven't seen one of these in action before, I'm almost certain you've helped train one. Have you ever gone to a website and been asked which of these images has a car in them, or which of these images has a crosswalk in them? You were providing training data for convolutional neural networks when you did that. If you want to learn how to make your own convolutional neural networks, or if you just want to know why they work and don't work, stick around. This video is going to have you using one by the end, and it's easier than you think. Today's tutorial is a quick start guide for convolutional neural networks. If you're more interested in an in-depth tutorial, I'm working on one of those, and you can get to it by clicking beside me when it's available. If you're interested in a more general overview about neural networks in MATLAB, I have a couple of those, and I'm posting them in the description below. So let's get started. What is a convolutional neural net? For this tutorial, we're going to focus on a classic problem in convolutional neural nets: handwritten digit recognition. This problem is important because it relates to automatic reading of forms and letter mail, where, for example, you might like to know what the zip code is on a letter in order to be able to sort mail automatically without a human intervening. Conveniently, MATLAB comes with a data set for this problem. So let's take a look at an example. Here we see the number 2, and you can see that it's a 28 by 28 pixel image. In a traditional neural net, each of these 28 by 28 pixels goes into an input node, meaning that the first layer of our neural net has 784 input parameters. This is a bit of a problem because it means that we are generating an enormous number of parameters in the total neural network, usually measured in the thousands and sometimes tens of thousands. However, we can see that this is an incredibly inefficient design for this network. If I take my number 2 and I shift it just a little bit to the left or the right, you'll notice that totally different pixels are illuminated, which means totally different neurons are being activated. This difference results in an enormous waste of learning potential by the network because the network has to learn that it doesn't matter where the number 2 is and that it has to encode it into its neural network framework. However, I can achieve this property called translation invariance by using a convolutional neural network. In this case, we're going to use a large number of filters. Each filter is essentially a 3x3 or 5x5 set of parameters which allow a value to be calculated at each location along the image. Essentially, these will encode for patterns that the neural net is looking for at a local level in the image. It will then scan each filter across the image to produce an output set of neurons. Now, you might be wondering, if it's producing an output for every location, where's the savings? And the answer is that the parameters don't change depending on where you are in the image. So if you have learned a 5x5 filter, it has 25 parameters, but the same 25 are used regardless of what happens to the image. And so if you move your number 2, it activates exactly the same amount on the next layer, even if it's in a slightly different location. This savings and generation of translation invariance actually provides a number of benefits, not least of which, with only 100 or 200 parameters, we can achieve a very accurate result on this problem, whereas you would need thousands to get a comparable result from a traditional neural network. It also gives us benefits in terms of the amount of time it takes to train and the overall accuracy capable from this network at all. So I think that this is all a little bit esoteric. It's helpful to look at an explanatory picture to really get an idea of how you should think about how these are working. The best way to think about a convolutional filter is that it's a pattern matching tool. I can create filters which look for vertical or horizontal edges, for example. These filters then produce outputs which are fed into another layer. So here, for example, I show the results for a number 2 and a number 3 through vertical and horizontal filters. You see that they produce very different outputs. I can then create a filter which looks for these distributions at the next layer and make a fairly good 2-layer convolutional neural network. However, this is just a useful way to think about what the neural network is doing. It learns the optimal filters at each stage. I once read that this is describing finding its own best basis to work in for the image. The problem with this is that we don't actually know whether this is what the neural network did. It will choose the simplest, most robust method to get the highest accuracy. Reading too deeply into what a deep neural net is doing is very difficult to do. This is why they're called black box models. We can make our guesses as to how they work, but the truth is no one will know for a specific neural net, and you certainly won't know for all neural nets what they choose to do. For the code in this data set, if you're interested in following on your own, I'm actually going to upload it to a GitHub in the description below. You can also find a similar example on MathWorks' own website, which I'm going to link as well. It uses the same data set, but I've made some modifications and otherwise tweaked it to make it more appropriate for the tutorial I wanted to give. This might give you a different perspective on it if that's a thing you're interested in. So what is this actually doing? We're basically just loading an image data store. So what is an image data store object? Well, let's take a look. I see basically it's a list of files and it's a list of labels. This is the X value for the data and the Y value for the data. So how do you actually define one? Well, here you can see we just actually gave it a specific folder location and essentially said, look inside the folder for the information you need. So let's take a look at that folder. You can see it's just a folder with one subfolder for each class. If I look inside them, it just has the digits inside. So this is a really easy way to create a data set without really needing to encode all of the metadata anywhere. What's more, you can actually read the different pieces of the data set out and work with them if you want. It's actually really convenient. So for example, I can display a figure of, let's say, a number 2. So I can do imds.files, and they're in order. So the number 2 works, and there it is. I just pulled probably the 6th example of the number 2 out of the data set. So it's a very easy way to organize all of your data. The next thing we need to do is to create our train test split. We do this using a built-in function called split-each-label. This built-in function takes the parent data set and splits it into smaller pieces for train, test, and validation. In this case, we're doing 60% train and 20% each for validation and test. The training set will be used for setting the coefficients and parameters of our model. The validation data set is going to be used for detecting overfitting. This is a process called early stopping, which we'll come back to later, but basically is an alarm bell that rings when the model starts to memorize features of the training data set that aren't present in the validation data set. It's a sign that we need to stop training our model because it's as good as it's likely to get. The test data set is held off until the very end, where we use it for evaluating the performance of our model, but never at any point do we use it during the training of the model. A common mistake that new machine learning engineers make is using their test data set multiple times to evaluate different models. This sounds like a good thing to do, but what you've really done is just created a second validation data set. The next thing we need to do is define the architecture for our neural network. We do this by creating a list of layers. In this list of layers, we're going to have a few steps that I don't want to spend too much time on for mathematical reasons. These include the batch normalization layer, as well as exactly what the softmax and classification layers are doing. The first thing we do is create an input layer. This is essentially telling the neural network what sort of input to expect. In this case, 28 by 28 pixels with a single color channel. We then run this through a convolutional 2D filter. In this case, we're telling the neural network that we're going to be using 3 by 3 filters, and there will be 10 total filters. Because it's a 3 by 3 filter, there are going to be 9 parameters, plus we also have one bias term added in, resulting in 10 total parameters per filter. Each of these 10 filters results in a channel, so we now have an output space which is 28 by 28 by 10 channels. These 10 channels then run through a Relu layer. Relu layers are a type of activation function. They basically introduce nonlinearity into the system. They do this by taking any inputs less than 0 and forcing them to 0. Any inputs greater than 0 continue to be their original value. This nonlinearity is quite simple, but it's a very popular activation function because it's relatively well behaved while you're training and also gives you a wide range of outputs. The next layer we're going to need is a Max2d layer. This acts to decrease the size of our internal neural network in order to keep our memory and calculation time low. We have a 28 by 28 by 10 input space. What this will do is for every 2 by 2 region, compress that down to a 1 by 1 region by selecting the maximum value. This also helps deal with slightly different distance features from each other and other such behavior that's sort of undesirable in the image. We're then going to essentially repeat this process through a second layer of the neural network. We have again a convolutional filter with 3 by 3 inputs and 10 filters. The output again is in fact 10 channels. So this time, instead of having 3 by 3 by 1 parameters, we have 3 by 3 by 10, i.e. there's an input parameter for each of the input channels. This is then fed into a second Relu layer to provide a little bit of additional nonlinearity. We finally need to have an output structure which matches the number of classes. In this case, we have the digits 0 through 9, so we have 10 output classes, and we have 10 output nodes for the fully connected layer. This fully connected layer has neurons connected everywhere in the underlying image, so this results in an enormous number of output parameters to learn. We run this then through a softmax layer and a classification layer, which essentially are responsible for both telling MATLAB what kind of cost function it should be using, as well as making sure that the probabilities are being correctly calculated at the final step for the cross-entropy cost function that is being used behind the scenes. I'm going to skip out on a little bit of the math at this point because that wasn't what I wanted to focus on this tutorial. But as I said, I'm working on a more in-depth tutorial to deal with the details behind the scenes here. Now that we've set up our neural networks, the last thing to do is train our model and then test it on our test data set. We can do that with the following code. As you can see, this code starts out by defining the option structure. This option structure is not comprehensive. There's a lot of other things we could put in here, and it mostly controls the optimization and training settings. I'm not going to go over all of the different settings here, but I do want to point out the max epochs. This is an important option because we want it set high enough that the neural network is fully trained. You don't want to have a neural network not be fully converged in its training, otherwise you don't know what its final performance is. As you can see, after only 45 lines of code, we have a training for a convolutional neural network that will produce a pretty good result. Let's go ahead and actually just try this training process now. As you can see on screen, we are calculating not only the performance for the training set, but also the validation set. You'll notice on the side that we have a patience under the validation heading. This is essentially the amount of time that the validation set is allowed to get worse for before it triggers the early stopping criterion. We want to make sure that our iterations are set up so that it has time to hit the early stopping criterion rather than stopping because of the maximum time limit or the maximum iteration limit. As you can see, the training took about 1 minute and 47 seconds and used 24 of 100 available epochs. The final validation accuracy was 99.35%, which is exceptionally good for a digit recognition problem. However, I would expect a worse accuracy in general for a real data set as opposed to this evidently very clean data set that MATLAB provides. The final step in evaluating our model is to use the test data set in order to find the accuracy on data which was never used during the training process. The validation accuracy is not really representative because we stopped training once the validation accuracy started to diminish. This is really what you would call information leakage. There's a little bit of the validation training set inside of the actual final trained model. It's not directly been used anywhere, but on the other hand, we did kind of guarantee that we would work well on the validation data set, so let's try the test data set. The next section of code actually does exactly that. We use the built-in classify method in order to actually calculate the digits for the entire test dataset, and then we count how many times they disagree as a percentage. If we do this, we see that our current accuracy is actually higher for the test dataset. This is a good indication that the model is not overfitting, or that at least the validation dataset well represents the test dataset and is what we would like to see. We can also take a look at the specific examples within the test dataset which were underperforming. Ideally, you would be doing this with the validation dataset rather than the test dataset, but it's where we are at the moment. If I take a look, first of all, at how many of them there are, we see that there are, in fact, 9 such examples. If we visualize the 9 cases that the test dataset gets wrong, we see that it is predominantly 2s, 3s, and 8s being confused with each other. If you kind of squint at these for a bit with the video paused, I think you'll recognize why the dataset is struggling with these specific numbers. For instance, I can see that the 7 actual in the middle of this does look like it could be a 1. That's especially, remember, this data set includes a lot of rotated digits. That makes a lot of sense to me. There are only 9 examples where our model wasn't able to accurately predict this. While this is, I think, a cleaner data set than, say, the MNIST data set, which is more popularly used for this, I do think that this is representative of the type of accuracy that you can achieve even on a more difficult training case, if you are willing to put in a little extra effort in making the neural network robust. While this was a very challenging problem when it was first studied, at this point I think we have a pretty good grasp of being able to read at least isolated handwritten digits. So in the next part of this YouTube video, I would like to discuss some of the limitations of convolutional neural nets and training them in a supervised fashion. To illustrate some of the downsides to just naively training a model like this, let's imagine a situation where we were going to train a neural network to distinguish between a stop sign and a yield sign. Does the neural network learn to look for triangles and octagons? Or does it learn to look for a red color? Or does it learn to look for the word stop versus triangles? What exactly is it searching for? This question is really important because when we talk about an adversarial attack, that is, if somebody decides they're going to vandalize one of these signs, what do they need to do in order to make the self-driving car no longer recognize it as a stop sign or as a yield sign? It turns out that many existing solutions today fail when somebody places even a small amount of vandalism on a stop sign. This is incredibly dangerous and is a challenge that has to be overcome by these manufacturers before we can trust these vehicles autonomously on the road. This approach reflects a basic truth about machine learning. The machine learning algorithm is only as good as the data that you use to train it. So if you have only put in pristine stop signs and pristine yield signs taken with a professional camera where there is no rain, well, of course the model can handle those, but the first time it sees a snow-covered stop sign, it doesn't know what it's looking at. Or the first time some joker decides to spray paint a triangle on top of a stop sign, it gets confused. No human is going to be confused by a little bit of spray paint on top of a stop sign, but maybe a self-driving car will be, and this is something that these manufacturers need to take into account, because I guarantee there are stop signs which are not actually in the correct form and shape on the road today. I'm sure we've all seen vandalized traffic signs. So with that in mind though, this tool is still incredibly powerful and is able to learn patterns in the data we give it. You just need to know where you can apply it safely. Thank you so much for hanging out with us today, guys. If you enjoyed this video, why don't you let us know in the comments below? Or if we weren't clear about things, let us know that too. We're releasing several video game AI videos in the next couple of weeks, and I'm very excited about those. So if you're interested in them, don't forget to subscribe to the channel and check us out next week. Thank you so much, and I'll see you next time.